Okay, so a lot of the questions, if I remember these questions from 2.1, I feel like a lot of this is going to relate to each other. So we've got these questions about energy. 2.1, we got to look at what these questions are, but then also the Rydberg equation. So starting with just this conceptual one, there's a couple different ways we can deal with it, right? So when we're dealing with, what's problem 6 say? If I remember, you said problem 6 relates to this. So we're going to look at 2.1, number 6.
I have it.
Yeah, what you got?
What is the energy in joules of a photon with wavelength 720 nanometers?
Okay, so here's essentially what's going on, why we have to do the unit conversion. Most of you, when you write this down, you write E equals 6.626 times 10 to the minus 34 times 2.99 times 10 to the 8 divided by 720. And do you see what mistake I've made in this, just in terms of what we do in a chemistry class instead of a math class?
Like units.
Units. I haven't written down any of the units. Planck's constant is joules seconds. Speed of light is meters per second. This 720 is now in nanometers. So right away you can see, oh, my meters and my nanometers aren't matching up. There's actually two ways you can fix this. We could convert the speed of light into nanometers per second. That would work. And then this would be 2.99 times 10 to the 17 nanometers per second. That would work. Most people don't do that because it's the speed of light. It's always written the same way. So we convert our wavelengths. Since we will get the wavelengths, we won't always get the wavelength in nanometers.
Mm-hmm.
In our class, where we're usually dealing with speed of light type situation or visible spectrum stuff, we're usually going to be in nanometers. But you know, if you're doing different classes with different wavelengths, it might not be nanometers.
Okay.
Which means you'd have to convert the speed of light to multiple different things depending on the problem.
Okay.
It's like, no, let's just convert the wavelength.
I was just confused because I thought that wavelength had to be measured in nanometers.
No, it's just convenient in nanometers, right? For me, because this is going to convert, I do this conversion pretty easy. We can just do 720 times 10 to the minus 9. That's what nano means, meters, right? So once we practice the unit conversion, it becomes a lot easier. I see that nano and I just erase the n and put times 10 to the minus 9.
Okay.
And the unit conversions become really easy. If we write this down in meters, I can put this with 2 decimal places over. This is going to be 7.2 times 10 to the minus 7. So the convenience of it is when we talk about wavelength, for the do you remember the range of the visible spectrum?
Remember you saying?
Yeah. So I'll just say it again, right? The range of the visible spectrum is 400 to 700 nanometers. And that's way easier for me to say and remember than 4 times 10 to the minus 7 meters to 7 times 10 to the minus 7 meters. Right? Just in the words that I'm saying, 400 to 700 is way easier than 4 times 10 to the minus 7 to 7 times 10 to the minus 7.
Wait, times negative 10 to the negative 7 or negative 9?
Well, to the negative 7 for the meters, but that's why it's 400 nanometers, would be 4 times 10 to the minus 7 meters. So if this was 720 nanometers, I could leave it as 720 times 10 to the minus 9, or I can convert it to 7.2 times 10 to the minus 7. Either one will work when you punch it into your calculator. And for me, conceptually, it's easier to just erase the nano and put times 10 to the minus 9. Same thing when I do micromolarity. You know how we had something that was like 10.25 micromolarity?
Mm-hmm.
I just, in my head, I just erased the micro and put times 10 to the minus 6. Right?
When you're converting, I don't know if I was watching a YouTube video that just like was not accurate. They were saying like when you convert like micro to micromolar to just like straight up molarity or whatever, then you get rid of the negative in an equation. Is it just
Okay, so
I don't know what I was looking at.
it depends on what they mean by get rid of the negative in an equation.
Was it like they were moving it to the bottom or something?
Yeah.
Okay.
Right. So
You just always keep it.
and this is where the way we've been converting units so far has been where we write down, let's say we've got 10.25 micromolarity, and then I'm going to multiply by like 1 molarity is 1 times 10 to the 6 micromolarity.
Okay.
Or I could do it as 10.25 micromolarity times 1 times 10 to the minus 6 molarity per 1 micromolarity. Both things are true, right? And so what they were probably saying is like, oh, you put it to the bottom and you get rid of the negative sign because you're just doing an inverse.
Yeah. Okay. I just need to.
That's what I like. Unless the video was just totally wrong.
No, it's what that was.
But that's how I make. But you notice the way I do it, I kind of don't even do the fraction anymore. Once you practice this, I'm just like, oh, I'm just going to erase that and put a 10 to the minus 6 in.
Yeah.
Okay, yeah, that's what I was asking, if that's what you were showing before, just
Yeah.
like cutting that stuff.
So I just cut that step, and I just do it like this. I do 10.25 micromolarity, and then I just erase the micro, and I'm like 10 to the minus 6 molarity. Right? I'm doing this, but I just do it in my head because I've had enough practice. That's the same way I was able to convert my nanometers to meters so quickly, because I know nano just means 10 to the minus 9 of meters.
Okay.
Now, let's go ahead and finish this problem out before we move on to the next one, because important thing to remember, what energy scale should we get? Oh, that's the unit. Do you remember the scale for photons we talked about yesterday? You might not remember.
No. Out of curiosity, like the midterm for this class is basically just going to be questions like this. It's not going to be like.
There's going to be a written section as well. Free response section as well, yeah. I'm going to write down this number and we're going to see. So do you remember the energy scale we expect? Anyone? Photon energy is usually about... That's why we're finishing this problem, just as a reminder, right? And having that, now, we could have much bigger or much smaller wavelengths and we can get very different energies, but generally when we're doing the energy of a photon, a single photon, we're usually going to end up with things that are like this. This is 2.60 times 10 to the minus 19 joules. The energy scale we usually get for single photons, and for most things on the atomic scale, are on the order of 10 to the minus 19, 10 to the minus 20, 10 to the minus 18, that kind of range for energy. So when we get an energy that's on the scale of negative 21 to negative 18, we're like, okay, that makes sense. If you get something that's like negative 27 or positive 27 or anything that's really far off from negative 19, you probably did something wrong. Or it's asking you for, instead of doing this, and sometimes I'll write down the units on this, since this is a single photon, I'll write this as joules per photon. But that's kind of implied because this is the energy of a photon, so that's the energy of one photon. Sometimes they'll do problems where it's like, oh, how many joules in a mole of photons? And then you're multiplying by Avogadro's number, and you get something that's like the kilojoule scale. But if we're talking individual photons, individual electrons, individual atoms, 10 to the minus 19 joules is our usual energy scale. As a reminder, why do we switch units? Starts with a C. Convenience, right? We usually switch, you knew it, you just didn't want to say it.
No, I didn't.
Oh, okay. We usually switch units because of convenience. The reason that we switch instead of, instead of saying 7.2 times 10 to the minus 7 meters, we say 720 nanometers is because human brain does better with numbers between 1 and 1,000. So when we start looking at this, when we start talking about mass scale, come and grab a chair. There's chairs back there. There's a chair up here. When we start talking about the mass scale, we don't want to say what's the number? We don't often want to say, where is it even? We often don't want to say 1.66 times 10 to the minus 27 kilograms. So we just say 1 AMU. We could convert this energy into the convenient energy scale for the atomic scale, 1 electron volt. And 1 electron volt is 1.602 times 10 to the minus 19. So you can look at the equation sheet, right? This is part of one of the benefits of getting not just familiar with these things, but kind of understanding them. Like the EV on an electron volt on the equation sheet kind of gives you the atomic scale standard energy. So anything that's around that amount of energy makes sense on an atomic scale. Atomic mass, things on the order of 10 to the minus 27 kilograms or minus 24 grams. Oh, sorry, 24 grams. Right? That would be the standard mass on the atomic scale. And it's already on the equation sheet if we know to look for it. So if you ever get an energy that's way off from that, you're either doing like billions of atoms together or you made a big mistake.
So we should just use that as like a reference point?
As a reference point, yeah.
Okay.
Now, the most common mistake people make, and we talked about this in class yesterday as well, the most common mistake people make is if you are doing this in your calculator and you don't do parentheses on the bottom, this 10 to the minus 9 ends up top instead of on bottom. So just make sure you're, because like yesterday in class, I went around the room and I saw a bunch of people who, perfect setups. They had it written exactly like this without the parenthesis, and they were getting complete nonsense answers. And they're like, I don't understand what's going on. And I'm like, oh, they're like, I got everything right. It's like, show me your calculator. And in their calculator, they don't have the parentheses, and it's just messing up their calculation. Which is why I stress, if you don't have a calculator you're practicing with yet, get a calculator ASAP and start doing all of your homework with that calculator. Bring it to class. You don't want the midterm to be the first time you're trying to use a calculator. It's a mess. I mean, it's doable, but it's just more stress than you need when you're trying to do a midterm. So find the calculator you like and practice with it. So that was number 6, and that was also kind of addressing this idea of why do we do that unit conversion for energy. Let's go ahead, let's keep going through 2.1 since I think that's more pressing for people, and we'll get to the 2.2 questions in just a little bit. Who's got number 8 for me? And I'm going to erase this. No other questions on this? Okay. Who's got number 8 for me?
What is the energy in kilojoules of a mole of photons with lambda equals 720 nanometers?
Oh, I shouldn't have erased that. It's the same as a continuation of the same question. Okay, and this gets to the exact thing I was just talking about. Okay, so we've got the energy of a photon for that 720 nanometers. Can I remember? Did anyone write it down? Do I need to pause and check my video? No. Is that it? 2.60? Yeah. Okay. So we got this 2.60 times 10 to the minus 19 joules per 1 photon. Right? That unit of per 1 photon is not written down, it's just implied. Right? Because this is the energy of a photon, you don't need to write of a photon. But in this problem, that's actually going to be kind of useful. Now, it's not asking for a single photon, it's asking for a mole of photons, right? Is that what it said? And it wants the answer in
Joules.
Kilojoules. The units are often a hint, right? When it's asking for a particular unit, it's either the standard unit we use, it's the standard unit for that constant, or it's going to be convenient for that calculation. So if I get something that's like 50 trillion kilojoules, I'm going to be like, that's weird. If I get something that's like 10 to the minus 22 kilojoules, that's going to be, I'm guessing that whatever I get is going to be between 1 and 1,000. Because it's the kilojoule scale. Why would they ask me to put it in kilojoules? Unless it was like that first 1.1 homework assignment where we were just doing a lot of conversions. That's probably a hint. So let's go ahead and do some thinking. Now, we already know the energy for 1 photon, 2.60 times 10 to the minus 19 joules per 1 photon. And then we can say, okay, We want it to be per a mole of energy per mole of photon, so I'm going to have 1 mole on bottom. How many photons in 1 mole? What's the number for a mole? Avogadro's number. 6.02 times 10 to the positive 23rd photons. So notice my units of photons is going to cancel out, and I'm going to get some amount of energy for a huge number of photons. Each photon by itself carries an itty-bitty, really tiny amount of energy. But if I've got a mole of them, which is a big number of them, but they're really small, but if I put enough of them together, like these lights are probably kicking out moles of energy over a certain amount of time. But like, I just do this multiplication, and we'll see if we get something that makes sense for the kilojoule scale. Practice with your calculator if you haven't been practicing with your calculator yet. 2.60 times 7 I have to be really careful. My hand always wants to hit the negative exponent because it's so common in chemistry. So I got 156,572. Too many sig figs, but when I cut that down, it's 156, 157. If I'm being correct with my significant figures, I only kept 3 sig figs here. This would be 157 kilojoules. And notice 157 makes sense on the kilojoule scale. They could have had it. They could have not given us that hint and left it in joules, and it would have been 157,000 joules. But the kilojoules is just easier to work with. That's why it had us switch that unit. So pay attention to the units they're asking for. From here on out, the units they're asking for are no longer just like, we want to see if you can do it. It's actually the most convenient way to write down the number. Okay. So that one kind of related to the stuff we were already looking at. But now I think we're shifting pretty dramatically. Were 16 and 17 graded problems?
Yeah.
What were they? Were they similar to this?
I remember being able to do, I don't remember how similar, but I remember being able to do like the non-graded ones pretty easily.
Uh-huh.
And those took me probably like 20 tries to figure out.
Whoa.
Yeah,
okay.
but yeah.
Are we ready for me to erase this and move on? And are these questions, do you have specific questions as well? Or?
I had some written down. I can look.
Cool.
For some,
Yeah. Oh, we'll just, so this is the list that we're going through, and then we can do more. So if yours is already on this list, okay, we'll get to it. Otherwise, we can add to it once we get to the bottom. Okay, moving on to number 16 and number 17. What's number 16?
Number 16 says, what is the energy in joules of a photon where the wavelength of light is 591 nanometers? So I think it's just like question 6.
Yeah, it's question 6.
So it's
right?
just a repeat of question 6.
Repeat of question 6. We can still do it together real quick. It's the energy of a single photon at 519 nanometers, so it's going to be 6.626 times 10 to the minus 34 joules seconds times 2.99 times 10 to the 8 meters per second divided by 591 times 10 to the minus 9 meters. Notice how fast I'm doing those unit conversions in my head now.
Yeah.
Right? I'm just erasing that nano and putting 10 to the minus 9. Technically, we can move the decimal place over and make it 5.91 times 10 to the minus 7, but this is faster for me. 591 times 10 to the minus 9.
And we converted that because then it's going to like cross out
Meters and meters.
Okay,
yeah.
I think
Have
that's
that
what got
unit
me,
connection.
was just, like, actually even
Do you know what
setting it up.
answer you put in?
Yeah, I got it. I think I got it right, but I said 3.36 E negative 19.
Yeah, that makes sense, right?
Okay.
You guys. So the most common mistake, if you forget to convert to nanometers, you usually you would have ended up with 3.36 times 10 to the minus 27.
Okay. And we want it around that 19.
And that minus 27 instead of 19 is because a factor of 9.
Okay.
You're just off, like, so a lot of people are off by a factor of 1 billion.
Okay.
Which is fine. It's just you forgot your nano. But no, that sounds like a right answer. Right? So it was probably that meters conversion was messing with you. I think number 17 is the tricky one that no one has asked me about this quarter.
Yeah, I think it's this one that really took me forever.
Is it the photons per second?
Yeah. I had to research to how to do it.
So it's kind of like, it's literally the problem. So we just did that problem, but we did it in 2 steps, and this puts the 2 steps together into 1 step. Right? So it was like the calculate the energy of the photon and then the number of photons. And we just did that, but we did it in 2. We did it in number 6 and number 8. And number 17 is both of those together.
Okay.
So what we just did was we said energy of a photon times the number of photons equals energy total. Right? That was the calculation we just did in number 8. Right? We took our energy of photon. We only had 1 mole, so we just multiplied by Avogadro's number for our number of photons. And then we get our total energy. We're about to do the same thing with this problem, but we're putting number 6 and number 8 together into 1 problem. And so we're going to try to separate that out in our head. So let's go ahead. Let's get the words for number 17. And there was an earlier problem that was like this, but let's just do number 17 together. We'll do your particular numbers as well, because everyone will have different numbers for this.
17 was how many photons are emitted each second by a 10 milliwatt? I don't know if that's the correct.
Yeah, that's right.
1.104 e to 3 nanometers light source.
What was the 1 point?
1.104 times 10 to the third.
10 to the
Third.
positive 3
Yeah,
nanometers.
light source.
Okay. So we can kind of see these different parts here. And then does it give you the other hint in the problem? Does it tell you what watts is?
No, it was a secret.
No, that's given in the earlier part of the homework.
Earlier?
Yeah. So if you didn't do, and I can't remember which number it is, I think it's number 15. If you didn't do number 15, you might have missed that detail. So that extra detail in number 15 is 1 watt equals 1 joule per a second. Now, there's one other piece of information I don't think you read. How many photons by 10 milliwatt power
Each
source
second.
per a second?
Sorry.
Right, so that becomes really important. So, I'm gonna do my thing that I do. Right, I'm gonna break it down because this is a tricky problem. Those earlier problems, I didn't feel the need to do it because they seemed pretty straightforward. This one is definitely tricky. So I'm gonna write down my explicit information. 10 milliwatts. 1 second, wavelength, and I'm going to write this down a little bit different. 1104 nanometers. I don't want the scientific notation on top of the scientific notation. That's all of my explicit information. The result I want is a number of photons. Implied information. 1 watt equals 1 joule per a second. Not given anywhere explicitly in the problem, but it was earlier in the problem.
I think I just didn't.
And it's one of those
connect that.
things that I hope you know from high school physics.
I didn't take physics.
Oh, well.
Yeah.
Then it's in the earlier problems, right? Okay. The other thing, energy of the photon is hc over lambda. And then the energy total is going to be the number of photons times the energy of each individual photon. Right? Kind of like what we did in number 8, which is where I've got that note up above in blue. So at this point, after we have that implied information is tricky, right? You don't know that stuff just by looking at the problem. But when I write it down, none of it is really revolutionary. Now all we have to do is figure out the right way to put all of this information together to get to the thing that we're looking for. The thing that we're looking for in this situation is n. So the first thing I can recognize is, oh, and there's one more thing that we need to know. 1 nanometer, 2 more things we have to know. Unit conversions equals 1 times 10 to the minus 9 meters, and then 1 milliwatt equals 1 times 10 to the minus 3 watts, right? Those 2 unit conversion things, we also need to know those. I'm hoping at this point we do know those, but still not given in the problem, so it's still implied information. So, first thing I'm going to do is just do 1 second times 10 milliwatts. Notice the seconds will cancel out, and that will get me how much energy happens in 1 second. So I do 10 times 10 to the minus 3 watts, which is, I'm just going to plug it in there, which is joules per second times 1 second gives me 10 times 10 to the minus 3 joules. That's my total energy. Right? That's the total amount of energy that this little laser pointer is shooting out, or whatever this thing was. Was it a microwave laser pointer? Did it say? It doesn't matter, right? It's just a light source.
A light source.
Light source, okay, yeah. So some light source. One of the problems does it for a microwave. One of the problems does it for like a laser pointer. Light source is, if I'm randomly generating numbers, I usually just do light source because I don't want to say something that's a little bit off because the random number was off. Okay, so now that we've got our total amount of energy, I can just rearrange this equation, right? And I can say, I'm going to write this a little bit better now. I'm going to write this as 1 times 10 to the minus 2 joules divided by the energy of the photon equals the number of photons I have, right? So I just divided my photon energy over, multiplied by that.
Is it -2 or -3?
It's negative. It was 10 times 10 to the minus 3, which is just,
and then we're just
1
doing
times 10 to the
one,
minus
sorry.
2. I got tired. 10 times 10 looks weird to
Yeah.
me, so that one I wanted to change. And if I wanted to be more careful with my scientific notation, I could do it as 1.0 times 10 to the minus 2. But yeah, 10 times 10 looks weird to me.
Yeah.
So I just wanted to change that. Okay. Can we calculate the energy of 1 photon? Yeah, right? So we've used this piece, we haven't used wavelength yet.
So are we plugging wavelength?
Yeah, I do it in 2 steps. If I plug it all of the variables in there, I always mess up. So I just do my energy of a photon separate, and then I'll plug it in there. That's going to be my same problem we just did, 626 times 10 to the minus 34 times 2.99 times 10 to the 8 divided by 1104 times 10 to the minus 9. Right, that will get my photon energy. And you notice that part is just like we saw in number 6 and number 16. So hopefully we're getting pretty comfortable with that. 626 times 10 to the minus 34 times 2.99 times 68 divided by 1104 times 10 to the minus 9. Now this is a pretty big wavelength, so my energy should be a little bit on the small side. Oh, it's actually still not that small. I thought maybe it'd be down to the 10 to the minus 20 scale. But it's 1.79 times 10 to the minus 19 joules. Reasonable energy for what we expect. And I can even put per photon there, even though we don't need that. Now, if each photon carries 1.79 times 10 to the minus 19 joules, do we expect we're going to need a lot of photons or only a few photons to get up to like a joule? How much energy would we have if we had 10 photons?
Not a lot.
But like, what would the actual number be?
Like 10 times whatever that is?
Yeah.
Oh, okay.
What if we had 100 photons?
Then 100 times that?
What if we had 1 billion photons?
1 billion times that.
right? But even a billion photons would still be 1.79 times 10 to the minus 10 joules.
Yeah, it's still not.
So we're gonna need like way more than a billion photons. We're gonna expect this number to be a really big number. And that also makes sense because look, I'm gonna have this 10 to the minus 19 number on the bottom of a fraction. So I'm gonna expect 10 to the positive 19 of that number. Minus 2, stuff like that. But I'm gonna expect my n, my number of photons, to be like a really large number. So I'm going to plug that number in, 1.79 times 10 to the minus 19 joules. And also notice my units work out nicely. Joules and joules cancels, and I'll just get a number of things. So I do 1 times 10 to the minus 2 divided by 1.79 times 10 to the minus 19, and I get 5.5 times 10 to the positive 16. So I get this really big number, 5.5 times 10 to the positive 16. And you'll also notice, if you haven't noticed me start to do this, I will often explicitly put positive 16, or I think I did it earlier sometimes when I do my speed of light, I'll put the plus sign in front of the 8. Since chemistry so often has negative exponents, I put the positive exponent there to just be like, really don't miss that this is positive. Like, I didn't just drop a negative sign. It's supposed to be positive. So I'm guessing that would be, what number did you get?
Definitely not that. I got like 3.336 e to the 16. I'm not sure where I got
That's not far off.
Okay. Yeah,
So
I
it
tried.
could be that I have a typo someplace. Maybe I made a mistake. Maybe you made a mistake.
I highly doubt it.
But you're on the right track.
Yeah.
Well, I did it pretty quick.
I think I like had the right idea. It was just like the fact of like bringing all the ideas together.
Yeah. And you notice each of the steps I did by itself wasn't a big deal.
Yeah, because like we did them before several
Yeah.
times.
And that's where things in chemistry start to get really tricky, is especially in the next 2 weeks, pretty much like a little bit in our next class, but definitely like after, like material after the midterm. It's going to be like everything from the last few weeks, bit by bit, now all put together to start to talk about like molecules. And we're always going to try to find it like that, and this is part of why looking for, oh yeah, you missed a lot yesterday. This is part of why looking for patterns and recognizing patterns becomes so important, because there's too much stuff to think about if we don't see a pattern. So that whole idea of like the quantum numbers leading to the electron configurations being a pattern on the periodic table. So it's like, okay, I actually, once I understand that stuff, I don't need to think about every little thing every time. I can just look at the pattern on the periodic table and know it comes from the thing, from the thing, from the thing. And then we just go with the pattern that we recognize instead. It makes it a little bit easier. So that was a good kind of refresher on photon energy unit analysis kind of problem approach. Does that make us ready to tackle 2.2? Any other questions? Did you have any questions on 2.1 before we move on?
No.
Okay, so on to 2.2. We're going to start with number 7 and the mysterious disappearing negative sign. Right, and you'll find, should I tell you this? I'm recording this. Should I tell you this? I'm going to pause this for a sec. Okay, so looking at things like the Rydberg equation, that the kind of disappearing negative becomes a really important conceptual thing. So let's write down what 2.2 number 7 is first, and then we'll get into some conceptual thinking around it. What does 2.2 number 7 say?
What is the change in energy in joules for an electron in a hydrogen atom when it's excited from n equals 1 to n equals 5?
Okay, so we're looking at the change in hydrogen energy when we're excited from n equals 1 to n equals 5. One of the things we talked about last time is whenever we've got two n values, huge hint, Rydberg equation, right? So the Rydberg equation that we're going to use is we're going to use the delta E equals negative z squared RH times 1 over n final squared minus 1 over n initial squared. And I think, were you the person in class yesterday who kept squaring the negative away?
No.
Okay, that was somebody else. Which class are you in?
Yesterday.
6 to 9? Okay, so it was the same class. I think it was someone who's sitting at the same cluster as you.
Yeah.
I remember catching. It was someone who sits across from you.
me,
Yeah, because you two were talking a bunch, and like he had 3 answers where he thought the negative was inside the square. So I've started writing it with the parentheses like this, so you know that it's like, because when it's written as like negative z squared, everyone's like, oh.
Yeah.
It's like, no, I would have
So
put
the
parentheses.
negative's outside.
The negative is outside
Oh.
the square,
Gotcha.
right? It's just the z that gets squared.
What does the H mean in the formula?
The subscript h there?
Mm-hmm.
So it turns out, because there are multiple ways and multiple units that people have done Rydberg's equation in the past, that people actually feel the need to specify which version of the Rydberg constant they're using. So R sub h means it's the energy version of the Rydberg constant. If you look on the equations sheet, you'll see Rydberg constant RH, R sub h equals, right? So it's just that value. It's just the way we write down that constant.
Okay.
It technically stands for the Rydberg hydrogen constant, because technically it should be different if we're looking at something besides hydrogen. So it really just means the Rydberg hydrogen constant.
Okay.
But it's just a constant value. I also often like to put the subscript atom here to just make it clear that we're talking about the energy change of the atom. So if you were squaring your negative, that's where your negative sign was coming and going from. The other thing that I like to do before we get into, so at this point we can do the familiarity thing. I plug in my initial value, my final value, and solve. My initial value is going to be bigger than my final value, so this thing is going to end up, this parenthesis is going to end up being negative. The negatives are going to cancel. I should get something that's positive. I don't necessarily like thinking about it in the pure mathematics. I like to draw pictures. I just do better with pictures. So I draw my picture. I've got my n equals 1, my n equals 2, my n equals 3, my n equals 4, and my n equals 5. And then if I'm going from 1 to 5, I would draw an arrow going up. That arrow going up would mean my delta E better end up positive, right? I can logically think through my negatives and positives, and that way, at the end of the problem, if I get something negative, I know I messed up something. It could be my order of my 1 and my 2, it could be my negative sign out front, but I definitely messed something up. And so I like to do this kind of logical thinking before I start crunching things in my calculator. That lets me kind of figure out, should my atom energy, should my change in energy of the atom be positive or negative? Now, how does an atom gain energy? There's more than one right answer to this. How does an atom gain energy? What's one way I did it in class as a demo?
A reaction?
Yeah, from a reaction, a particular reaction. Do you remember what I did for my demo when I had the spray bottles?
Different chemicals?
I had different chemicals, but what I did to the chemicals?
Mixed them?
Lit them on fire.
Oh.
Right? Fire. So thermal energy is one way that we can put energy in. So those chemicals, they weren't glowing when they were just sitting in the bottle, but if I shot them through the fire gave them a moment where they had their increased energy, and then when they lost that energy again, we saw that flash of like red light or green light or whatever light we saw. So thermal energy is one way we could do it. Another way that we did in class yesterday when we were walking around with the glasses on, what did we do? Do you remember what you looked at with the glasses? Can you flip that switch real quick?
Electricity.
Electricity, okay, turn it back on, right? Electricity, right? The lamps didn't glow until we put electrical energy into them. That's another way we can get atoms to gain energy. We can put electrical energy into them. Technically, we could also do like kinetic energy, but that's pretty similar to thermal energy. The last one that is also important is what we call, if we want to sound really fancy, photonic energy. That's a fancy way of saying we shine light on it. Right? But you can put light energy into it. You can put photonic, because light's made of photons, and so you say photonic energy. That just means you're shining light on it. So there's 3 different ways that we could put energy into it. Most of the time when we're talking about atoms, we'll be looking at this in terms of the change in energy of the atom related to the energy of a photon being absorbed or emitted. So in this situation where the atom is gaining energy, it's gaining photon energy. So the photon energy and the atom gaining energy should be the same value. If we were dealing with an atom losing energy, going the opposite direction, right? Notice that magnitude is going to be the same value. Right? So whatever number we calculate, whether we do, what's the difference between 5,1 and 1,5? A negative sign. Right? So gaining energy and losing energy is going to have the same magnitude, but a different sign. The photon, though, when this atom loses energy, it loses energy by emitting a photon. The photon still ends up with positive energy. So in absorption, the atom and the photon have equal energy. In emission, the atom and the photon have equal but opposite energy. And that just has to do with the conservation of energy idea. Again, because this is a process. It's not like, it's a process. The photon is like disappearing into the atom and then coming back out of the atom. So it's that photon energy that's being conserved. But let's go ahead. So now that we've got the conceptual work, we're expecting a positive answer. Let's go ahead and just do the calculation real quick here. My delta E of atom is going to be, since this is hydrogen, Z is going to be equal to 1. That's going to be negative 1 times 2.18 times 10 to the minus 18 times, my final is 5, so I'm going to have 1 over 5 squared. My initial is 1, so I'm going to have 1 over 1 squared. This is going to be 1/25 minus 1. That is going to be equal to 24/25, which I don't know what that is in my head. So, sorry, what'd I forget? Negative 24/25. Right, and that's important because I'm expecting that negative sign and that negative sign to cancel out, so I end up with positive energy. So if I do 24 divided by 25, it's 0.96. So this is negative 0.96. I'm just going to erase all of that thinking now. This is going to be equal to negative 1 times 2.18 times 10 to the minus 19 times negative 0.96. Negative signs are going to cancel out, and then I just multiply this through. I'm going to get something really close to 2. Oh, we did this one in class yesterday too, didn't we? Is it 204?
209.
209. Okay, we did a different one in class. So we end up with 2.09 times 10 to the minus, and I switched that 19 to, ooh, talk about typos. Did you all see my crazy typo that I just did without even thinking about it? I switched my 18 to a 19 just because I'm so used to doing minus 19s for energy. So like, definitely, I actually did that on the board in class yesterday, and I had someone like 10 minutes later, we were doing sample problems, and someone was like, wow, how did you switch that from 18 to 19? And I was like, oh, it's just a typo.
I think that was me.
Oh, did you find that? Yeah. Because you were like
I
really,
remember that.
yeah. Oh, it's just me making a typo. I definitely make typos like that. So, I got a little lazy with my units. This is in units of joules. This is in units of joules. That's no units. That's no units. So I end up with 2.09. Positive 2.09 times 10 to the minus 18 joules. So, but the way that I make sure I don't mess up my negative signs, I always do the thinking step of like, is my atom are my n values going up or down? Is my atom gaining energy or losing energy? Photon should always be positive, right? Because it's the absolute value. So photon is always positive. But the atom can gain or lose energy. What question did you have from 2.2?
Can we go over number 11?
Yeah. Any other questions on this one before we go on to number 11?
10.
Oh, let's do 10 as well.
And then the F and the I just stand for final minus initial.
Final minus n initial. Yeah.
Thank you.
Your textbook sets up the Rydberg equation a little bit differently. I like this version better. I'm less likely to make mistakes when I think about my atom versus my photon. The original Rydberg equation, the one in the textbook, puts those two ideas together and then does a different weird thing to take care of the absolute value.
I don't know if you said it earlier in today's student hours, but you were talking last class about just like measurement expectations. I know you said like for energy, because I was able to make it the use like negative, like something to the power of negative venting is something that you should be seeing. Is there other like measurements for different things that would be?
For the molar absorptivity, that's something we talked about in the past. That one, if we're in units of molarity, should be typically between 10,000 and 100,000 molarity inverse centimeters.
Okay.
That was pretty common. When we're looking at wavelength, a lot of things are from 400 to 700 nanometers for the visible spectrum, but a lot of the wavelengths we look at are on the nanometer scale. It's clearly not the only scale. You can go into ultraviolet and gamma rays and X-rays. You can go down to radio waves and microwaves. But most of the stuff we look at is going to be in the nanometer scale, hundreds of nanometers for our wavelengths of light.
Okay.
And then our energies are often on the scale of -20 to -18 joules when we're dealing with individual atoms or individual electrons or individual photons. So when we're on that atomic scale, -19 joules is a really common energy scale we deal with.
Gotcha. Okay. Thank you.
And so those are the really common ones we have so far. I don't think I'm forgetting any yet, but maybe I am. Charge is always on the scale. Do I have that written down? Charge is also on the scale. I don't have that written down here. Charge is on the scale of like 10 to the minus 19 coulombs as well. And we just call it like 1 electron charge. But 1 electron charge is like 10 to the minus 19 coulombs.
Okay.
Yeah. Okay. So let's go ahead. Let's do number 10 and number 11. Any other questions on this? Let's see. We did number 7. 2.2, number 10. What does 2.2, number 10 ask us to do? Hey, come on and grab a chair. These are the questions I'm recording, by the way. These are the questions we've already gone through. We're getting on number 10 right now. Does anyone got number 10 handy?
Emission of a 1282 nanometer photon lowers an electron in hydrogen from n equals 5 to which quantum number n?
Okay. So number 10 is like number 7 backwards. I find doing the Rydberg equation backwards to be significantly more challenging for students than doing it forwards. Mostly because, again, we've got 2 n values. That's our big hint that we're doing like a Rydberg equation thing. So we've got our delta E of an atom is equal to negative z squared RH 1 over n final squared minus 1 over n initial squared. The reason that this is significantly more challenging for students is because all of a sudden the unknown variable we're trying to solve for has an inverse square to it. And that just creates a lot of algebraic headaches in a 127 class. So we went through one of these problems yesterday, but this is the kind of problem that you've got to try on your own like 3 or 4 times before you're like, I've got a pattern that works for me. And I get a good answer. Let's go ahead, let's do some thinking real quick before we jump into the math. The other thing we're going to need, there's 2 other things we need. We're going to need energy of the photon equals hc over lambda. And we're going to need that the change in energy of the atom, absolute value, equals energy of the photon. So essentially, I'm going to need to deal with that negative sign, and should it be there or should it not be there for the thing that we're dealing with. I forgot to write down one of the words in the problem. Can you read the problem again?
Emission of a...
That's it.
Emission.
That's a really important word in this process for the thinking process, right? So if it's emission, I know that my electron in this hydrogen atom is starting there and it's dropping down to something. My atom is definitely going to be losing energy. Right? That word emission lets me know that. If it was just 128 nanometer photon is associated with n equals 5 to n equals what, it could have been going up or down, right? If it didn't tell us it was emission, it could be 5 to 6, 5 to 7, 5 to 8. But since it's specifically emission, it's 5 to 4, 3, 2, 1, right? It's to one of those numbers. So in the, I don't want to deal with this mathematical way to do it, is try 5 to 4, try 5 to 3, try 5 to 2, try 5 to 1. One of those is going to be right. But let's try to do it the more kind of less guess and check way in the actual mathematical way. So I'm going to do this, again, finding the right pattern for you is really important. I'm going to kind of do this where I'm going to calculate my energy of my photon, then I'm going to do my logic with absolute value, then I'm going to solve for my n value. And that's just the pattern that works for me, is I turn my 128 nanometers, so step 1 for me, and you've got to practice your own way. Maybe you're like, no, I got a different way that works for me. This way just makes it so I don't mess up that negative sign, because we have to deal with the logic at some point of how we get rid of the absolute value. So step number 1, I'm going to do 6.626 times 10 to the minus 34 times 2.99 times 10 to the 8 divided by 1282 times 10 to the minus 9. My energy of the photon is equal to, I'm expecting something on the scale of 10 to the minus 19. Again, practice with your calculators. Can you get it done? I'll give you a minute, and then we'll see if you can get it done faster than me, because I know you're writing things still.
Is there another word for emissions that would be the opposite that we should look for?
Absorption. Right? So emission is your atom is losing energy and light's coming out of it. Absorption is your atom's gaining energy, light's coming into it.
Okay, thank you.
Yeah, and so recognizing those key terms that give us information about the process, those are really important key terms to get familiar with. Okay, 6.626 times 10 to the minus 34 times 2.99 times 10 to the 8 divided by 1282 times 10 to the minus 9. I got 1.545 times 10 to the minus 19 joules. Agreeing? You're nodding. Is that what you got? If you didn't do it in your calculator, that's okay, but I need at least 2 people to agree with me. Okay, cool. Because otherwise I don't trust my calculator work. That's part of why there's 2 reasons why I don't use calculators in class. Reason number 1 is when I try to use a calculator in front of the class, I always make typos. Reason number 2 is I need you all to do some work. Okay, so that gets me my photon energy. Now I'm going to do my logic thing and say, should this negative sign be here or not? And there's, you can grab this chair if you want, come on in. And if you want to scoot your chairs in, someone can take this chair too. Like, scoot in, come on in. So the logic here, there's kind of 2 different things to do. There's 2 different ways to think about the logic. I like thinking about it this way. I know my atom needs to lose energy, so I want to get rid of the negative sign of my atom losing energy. right? The other thing I can think about is my initial is 5, my final is going to be 4, 3, 2, 1. This parenthesis is going to be positive. So I'm going to go ahead, I'm going to get rid of this absolute value of the energy of the atom. So step 2 is logic. Right? I know my change in energy of the atom is less than 0. It's a negative value because it's losing energy. So step 3, I'm going to go ahead and do 1.545 times 10 to the minus 19 is equal to that got scrunched in the corner a little bit. Let me rewrite that. I don't like it when my numbers get scrunched in the corner. 1.545 times 10 to the minus 19 is equal to 1 times 2.18 times 10 to the minus 18. I think I had a typo there too. 1 over 25 minus 1 over n squared. All that. Oh wait, I got that wrong too. Whoops. My final is the thing I'm trying to solve for. 1 over n final squared minus 1 over 25. Right, that's my n initial is 5. That's my 25. The important thing here is my logic is why I got rid of that negative sign. Right? This absolute value and the fact that I knew my atom had to be losing energy, that negative sign disappeared so that my photon energy is equal to the opposite value of my atom changing energy. That negative sign, and whether that negative sign should be there or not be there because of the absolute value, is the part that for most students is the most difficult. If you leave that negative sign there, it totally ruins your calculation. And you end up getting weird fractions. Question?
Where did you get the 2.18 times 10 to the negative 18 number?
That is Rydberg's constant.
Okay.
So that's just a
what
constant
I
of the
assumed,
equation.
because I thought it was in the one we did before, but I assumed it
Yeah,
was.
so that is the R sub H, the
Okay.
Rydberg constant for hydrogen. That's that number. Okay. So my 1 squared comes from the fact that we've got the z value is hydrogen, so that's just z squared is just 1 squared, which is 1. The negative sign disappears because of my logic, because I know the energy of the atom is negative. And if I take the absolute value of a negative, it's the positive version of it. I can also look at the logic if I know that my n5 has to be going to a smaller number. So this thing in the parentheses is going to be a positive value. This whole, my right-hand side and my left-hand side are both positive, which is what I need for my photon energy to be real. So that logic step is really important. Okay.
So if it said absorption instead of emission, would you leave that negative sign there?
That negative sign, okay, so let me think about this. If it was absorption, yes, I would leave that negative sign there because this would be flipped, and that's where that negative sign would be going. Yeah. Okay. Yeah. Yeah. Okay, so I'm going to do one change to the equation I have written because I'm not a huge fan of fractions. 1 divided by 25, I'm going to change that to 0.04. Not a huge fan of fractions, so I'm just going to turn this into minus 0.04. Now my algebra becomes pretty simple. I'm going to take 1.545 times 10 to the minus 19, divide by 2.18 times 10 to the minus 18, add 0.04 to it, inverse it, take the square root, hopefully get a whole number. Do it step by step still. I don't have enough space to do that on this side of the board. What's on my other side of the board right now? Hey, I erased it. Great. Okay. So, what we've got is we've got
1.154 times 10 to the negative 19 equals 1 times 2.18 times 10 to the negative 18.
The rest I remember. Thanks. Okay. So divide that over 1.54 times 10 to the minus 19 divided by 2.18 times 10 to the minus 18 gets me 0.0706 is equal to 1 over n final squared minus 0.04. Add 0.04 to both sides, and I get 0.1106 is equal to 1 over n final squared. Cross multiply, so I get n final squared is equal to 9.038 square root of 9. Right, we want a whole number. So if I take the square root, I get 3.006. It's 3. It's supposed to be a whole number, an integer value. Right, and for me, that's the algebraic steps I take to make sure I don't mess up. You can imagine if I had that negative sign there, when I divide over, this whole thing would be negative. Then I'd be adding this number to it, and I'd probably still end up with a negative 0.03. Taking the square root of a negative number doesn't even make sense. So we got to be really careful about that logic for whether that negative sign should be there or not.
How did you get from 0.1106 to 9.038?
Cross multiply. So I brought the
Oh.
n final over and did 1 over 0.1106.
Okay.
And so like the in-between step there was doing n final squared equal to 1 over 0.1106. But again, I don't like fractions, so I just plugged that into my calculator and it gave me that.
Oh, okay. Thank you.
Right, and that I think is one of the things that messes with people the most is I see students all the time trying to like complete the square and thing like they're like trying to like turn this into a whole fraction or something.
Yeah.
I'm like, no, just plug it into your calculator, it'll turn it into a number for you. Okay, so that was number 10. This side is all just algebra. I know the algebra, it's important, we don't want to mess it up. But again, if we wanted to double check this, how could we double check it?
Putting 3 back in.
Plug in 3 there and see if we get the same energy, right? So I can just go ahead and do that. I can do 1 divided by 9 minus 0.04. That's dramatic. Times 2.18 times 10 to the minus 18. Oh, I did something wrong. 9 inverse minus 0.04. Oh yeah, I did something wrong. Okay. Times 2.18 times 10 to the minus 18. I get 1.55 times 10 to the minus 19. So I can do it backwards. I can plug in 3 and see if I get my original energy back. And I do.
Okay.
So probably did it right.
Perfect.
Question?
I was just wondering if you could check my work.
Was it for this problem or a different one?
It's a different problem.
Okay.
It's number 10 of the next last problem.
2.3. Oh, you're hard on 2.3. Okay, we'll look at that in just a moment, no problem. Let me do one more problem on 2.2, then we'll look at that. Any questions on this one, or are we ready to try number 11? Okay, I'm going to erase this because if I forget to erase the other side of the board, this stuff dries on really hard. Okay. So that was number 10. And that just leaves number 11 on our list of problems to do. Unless people want to, except let's go ahead and add 2.3, you said number 10? 2.3, number 10?
Yeah.
Okay. Add that to our list of problems to do. Okay. I'm going to erase this problem. Let's see what number 11 has for us. Does anyone have that handy?
Yeah, it's calculate the shortest wavelength in nanometers emitted by an electron and a hydrogen atom undergoing a transition from the n = 4 level.
Okay. Key terms that let us know it's Rydberg equation. Shortest wavelength, hydrogen, emission, all of those things. Now, in order to figure out the shortest wavelength, this one is a logic problem. So here's what we have here. We've got our same type of thing. We've got HC over lambda is equal to the absolute value of negative Z squared RH times 1 over n final squared minus 1 over n initial squared, and of absolute value. Now, it tells us the initial is n equals 4, and it says it wants the shortest wavelength to associated with that. So, again, logic. It tells us emission. So we know the answer is 3, 2, or 1. We've only got 3 options for our right answer here. So here's our n equals 4, n equals 3, n equals 2, n equals 1. Quick thing, I'm going to write this equation down to help us think of it. Is the shortest wavelength going to be the biggest change in energy or the smallest change in energy? Thumbs up for big, thumbs down for small. Energy of the photon, inverse relationship. So if we want the smallest wavelength, we want the biggest energy change. Right? So this would be big energy. Small wavelengths. This one, small energy, big wavelength. So again, this problem is trying to do the next level of thinking, right? I'm not just giving you n values and asking you to plug things in. I'm saying, hey, can you think through the meaning of this stuff? Can you think through the concepts of this? And figure out one of these values that I didn't tell you from the logic and the concept, not just me giving you numbers. So all we have to do, again, I draw the picture to think about it. I write this equation, so I'm like, okay, energy is inversely related to wavelength, right? Energy and wavelength are like 1 over each other. So my biggest energy gap, my biggest energy emission should be my smallest wavelength. So now I can just go ahead and plug things in. Now we're just doing something like number 7, where I'm going to have my wavelength in here. My atom is losing energy, so I'm going to need to get rid of that negative sign eventually. But I'm going to have -1. Let me write this in a different color. I'm going to plug things in, though, and I'm going to have -1 times 2.18 times 10 to the minus 19 times 1 over 1 squared minus 1 over 4 squared. Yes! Again, thank you. I think that's the 3rd or 4th time I've done that already. -18. Equal to 6.626. I don't have enough space to write all that out. Right, equal to HC over lambda. I can fit that in. 6.626 times 10 to the minus 34 times 3 times 10 to the 8 divided by lambda. I'm solving for lambda. Lambda is the only thing I don't know. That's an absolute value. So solve this side. If it's positive, leave it positive. If it's negative, make it positive. Then flip-flop. I don't like dividing over the numbers and leaving 1 over lambda. I'd rather cross-multiply and get my lambda on top as fast as possible. But again, we needed some picture. Well, I need a picture. Some of you can do the logic in your head. I need a picture to help me think through the logic of what my n values should be and whether my atom is gaining energy or losing energy. Some people, they practice this enough, and just the word emission, they're like, it's losing energy, it's going to be this value, done. Me, I always like to draw the pictures.
So say the question asked for instead of the shortest, the biggest, we would be hoping for a number in the red section. Like, not the red section, but like the small equals, small energy is big wavelength.
Yeah, that orange color, right? So that would be, we would use 4 and 3 would be our largest wavelength emitted. If it said largest wavelength absorbed,
Then it would be the one at the bottom.
absorbed,
Absorb means they're taking it in.
so it would be 4 to 5.
Oh, because it goes up.
I didn't
Oh,
even
yeah.
draw that, I only drew emission.
And then,
Smallest absorbed, 4 to infinity,
oh, okay.
right? So emission and absorption could be completely opposite. Like, I didn't even draw the absorption possibilities because the problem didn't ask about it.
Okay, but in the case that it was, it would just be.
Yeah. If it says the shortest absorption wavelength starting at n equals 4, since it's absorption, it would be 5, 6, 7, 8, 9, 10, 11, 12. It'd have to be one of those like numbers bigger than 4. So that one word, absorption versus emission, has a pretty big impact. Should I go ahead and finish out the problem? Okay, let's finish.
3 times 10 to the 8.
Yeah, I didn't have space to write 2.99. 3 is close enough. I need a little bit more space. I'm just gonna flip the board. Okay, let's go ahead and do all the algebra real quick. I'm expecting something in the infrared, so something that's like a couple thousand nanometers, like 1 to 2,000 nanometers. We've got 6.626 times 10 to the minus 34 times 2.99 times 10 to the 8 divided by wavelength, looks like x instead of lambda, is equal to absolute value -1 times 2.18 times 10 to the minus 18, I got it right that time, times 1 minus, what was it? 1/16. Perfect. Okay. First thing I'm going to do, grab my calculator, and absolute value. I'm going to take 16 and inverse it, 0.0625, so I'm going to turn that 1/16. Oh no, let me do this in 2 steps. So if I do 1 minus 1/16, this fraction becomes 0.9375. Multiply that by 2.18 times 10 to the minus 18, and I get -2.04 times 10 to the minus 18. Absolute value is just going to get rid of that negative sign, so I get 2.04 times 10 to the minus 18. Multiply my numbers up top together, 6.626 times 10 to the minus 8 is 1.981 times 10 to the minus 25 over lambda. And again, the way I like to do this is cross multiplying. Some people like to divide over, then inverse. I find it easier to cross multiply, so I get 1.981 times 10 to the minus 25 divided by 2.04 times 10 to the minus 18 is equal to lambda. Divided by 2.04 times 10 to the minus 18. Scientific notation. 9.71 times 10 to the minus 8, or 97 nanometers. Oh yeah, that's okay. I was thinking about the 4 to 3 instead of the 4 to 1. That's why I thought it should be infrared. 4 to 3 should be ultraviolet. We're okay. I freaked out in my head when I saw that number. And I dropped a 0.1 here. This should be 97.1 nanometers. Question?
When you're multiplying to get to nanometers, are you using 10 to the negative 9 or 10 to the 9?
Yes. Right, depends on which way I'm going. Since this was in meters, I was using 10 to the positive 9 to get it to nanometers.
Okay.
If I was in nanometers and getting it to meters, 10 to the negative 9.
Okay.
Right, and the conversion there, so let's look at that together for a second. 99.71 times 10 to the minus 8 meters. I can do this two different ways. I can do 1 nanometer for 1 times 10 to the minus 9 meters, dividing by 10 to the minus 9, which would be the same as 9.71 times 10 to the minus 8 meters, times 1 times 10 to the positive 9 nanometers for 1 meter. Those two things are mathematically equivalent. So dividing by -9 or multiplying by +9 should get us the same result. And then we have the exact same problem when we're going the other way, where it's like, are we using -9 or +9? It's like, well, are we multiplying or dividing? How did we set it up? And after a bit of practice, you just do it in your head. Right, so how did I do that so quickly? You bet, see ya. The way I did that so quickly in my head was I looked at 9.7 times 10, 9.71 times 10 to the minus 8, and I said that's 97.1 times 10 to the minus 9 meters. And that right there means nano to me. So I just said, oh, that's 97.1 nanometers. And so once you practice this a little bit more with the fractions, you'll start to be able to do it this way, where you see those 10 to the minus 9s, 10 to the minus 6s, and you just erase them to become nanos. Or vice versa, you see nano, and you're like, nano is just 97.1 times 10 to the minus 9 meters. Right? And so these three things, we just kind of are able to kind of do this, start to do this in our head a little bit. More practice first, though. Okay. Good on that?
Can you just explain how you know whether to use absolute value or not again?
So I always use absolute value. When I'm comparing photon energy to atom change energy, there's always an absolute value there. Right? And then the way I get rid of the absolute value is, in this case, I just said is my number negative or positive, I just applied the absolute value. The place where it's a little bit more tricky is if one of these was an unknown variable we were solving for, then the logical progress of like, do I expect a negative value or a positive value for my atom energy becomes a lot more important. And that, we saw that kind of logic in number 10. And we have to be really careful about that. But I always do. So I always use my energy of photon is equal to the change, absolute value of change in energy of the atom. And the reason it is like this is because the photon energy always has to be positive. The photon can be getting absorbed or emitted, but that photon after that process is always positive. If the photon is absorbed, that photon essentially loses energy to the atom, and the atom gains that energy. If it's emitted, then that photon is kind of gaining that amount of energy that the atom is losing. And so you still have conservation of energy. Question?
Did you do 10 for 2.1?
10 for 2.1? Yeah. Anything else on this one? Okay. Let me go ahead and do 2.3, number 10.
Oh, yeah.
Did I assign 2.3 already?
Not yet.
Okay. Are you getting me
Oh,
ahead?
what's a 2.2? Sorry.
It's 2.2. Yeah, that's why I was really surprised. I was like, I don't think 2.3 exists. I don't think there is a 2.3.
I think we did 10 maybe.
I think we did 10. We did 10. You were in the room when we were doing 10. What does number 10 say?
It was calculate the wavelength of the photon that is produced when the electron drops from n equals 7 to n equals 4.
Oh, we didn't do that one, but that's definitely on 2.2.
It's like on the electron configuration line at the bottom.
Oh, no, that is 2.3 or 3.1.
I'm not sure. I don't have my.
You don't have it. Okay, let me pause this real quick. Okay, so this isn't 2.3. I should have known. I didn't make it 2.3. It's 3.1. But we can look at 3.1 number 10, and we can also look at 2.1 number 10. Let's just do all the number 10s. We already did 2.2 number 10, and we might as well complete the set. I'm going to do 3.1 number 10 first because I feel like it's really closely related to the stuff we're doing. So let's go ahead and do that. Okay, so this one has pretty specific wording. Go ahead and read that again. Oh, you don't have it. Okay.
Calculate the wavelength in, I think it's mu and m. What is that?
Micrometers.
Micrometers, there you go. Of a photon that is produced when an electron in a hydrogen atom drops from n equals 8 to n equals 4.
So first thing I can recognize is emission. Right, because I'm going from a bigger number to a smaller number. Micrometers, because that's just how the energy works out. I'm expecting something to be 100 or 1,000 micrometers because of where this is. So it's not going to be visible, it's going to be infrared. Exact same setup. You each have different randomized numbers.
Okay.
So I think the numbers I had were different than that as well, but we should each have different randomized numbers. I'm going to do it for the 8 to 4, but it's going to be the same process. So I'm going to go ahead and set this up the same way we just did. HC over lambda is equal to the absolute value of -1 squared, already taken care of because it's hydrogen, times 2.18 times 10 to the minus 18. I finally am getting that right. From 2, so this is going to be 1/16 minus 1/64, right? 8 squared is 64, yeah?
I was looking at the other Rydberg equations, and it was like 1 over the wavelength.
I don't like that one.
Okay, so don't use it at all.
So that Rydberg equation, there's kind of two different changes they make. First off, you have to change which thing you're using. Like, okay, I'll just tell you this. All they do is they take the HC and they divide it over, so they have the HC over here. But they don't write that down. They change the constant to do that. So you have to use 1.07 times 10 to the positive 7.
That's what I wrote down.
Okay, yeah. I mean, that works.
Okay.
But then they do an extra thing. So to get rid of the absolute value, they say N1 has to be less than N2 to guarantee positivity. So they have this extra restriction on their logic when they do it that way. And I mean, we're essentially doing the exact same thing. Those two equations are equivalent. It's just where the HC is and how we're getting rid of the absolute value. So since we've already got these numbers, I find just kind of doing the logic to kind of be the best. N1 has to be smaller than N2. It's only for emission. Oh yeah. So in their problem, no, am I thinking of something wrong? Oh yeah. So in that equation from the textbook, they also drop this negative sign because they do a force here for the negative sign and they get rid of the absolute value in that negative sign because they always force this to be positive. So there's kind of like 3 changes you have to make to convert between the two. And rather than having 2 versions of the equation, I just like working with this one every time, and then I don't get mixed up in my logic and everything. So I do 1/16 minus 1/64 times 2.18 times 2.18 times 10 to the minus 18. And I get absolute value of -1.02 times 10 to the minus 19 joules. Great. Get rid of the absolute value by just getting rid of the negative sign, 1.02 times 10 to the minus 19 joules. It's equal to HC over lambda. The other thing I don't like is 1 over lambda messes with people for some reason. So now I just do my cross multiply thing again, where I get HC over 1.02 times 10 to the minus 19 is equal to lambda. With that other version of the equation, people always forget to do the inverse at the end. So then I just do inverse times 6.626 times 10 minus 34 times 2.99 times 10 to the 8th. And I get a value of 1.938 times 10 to the negative 6 meters. And now the fact that they ask for it in micrometers kind of makes sense, because what's micro mean?
10 to the
What's that?
10 to the 9.
That's nano. Micro.
10 to the 6.
Yeah. So this is just equal to 1.938 micrometers. I can just take that minus 6 away, and it's the micrometers now.
Okay, that's that's where I went wrong.
Just that last step?
Yeah.
Ah!
Oh my god.
Right, and again, I think you weren't here when I mentioned this earlier. Most of these problems from here on out, besides 1.1, when they ask for particular units, it's because those units are easier to use. So when it asks you for micrometers, you should expect an answer between 1 and 1,000 micrometers. If it asks for kilojoules, it's probably between 1 and 1,000 kilojoules. If it asks for joules, it's probably between 1 and 1,000 joules. Otherwise, it would ask for kilojoules. Right? So the fact that these problems ask for specific units is actually a hint in terms of what kind of answer you should be expecting. So that was 3.1, number 10. Let's go back a little bit. Any questions on this one?
How did you get 1.938 times 10 to the negative 6? You divided 1.
I did HC over that.
Okay.
Yeah, so I did 6.626 times 10 to the minus 34 times 2.99 times 10 to the 8th divided by 1.02 times 10 to the minus 19. Unless I messed it up in my calculator, but hopefully that was it.
Sorry.
It's also getting recorded, so you can
Oh,
watch it
yeah.
on YouTube later too. In case the picture's not very good. 2.1, number 10? Ready for it? Okay. And then, I don't know what time it is, but I feel like it's almost time.
3:42.
Yeah, okay, good, it's almost time. Okay, so probably the last one we're going to do, 2.1, number 10. You want to go ahead and read that one to me?
Yes.
The suspense. Could be anything.
Okay, what is the wavelength in micrometers of a photon frequency of 1.8 times 10 to the 12 seconds negative? Like, seconds
1.8 times 10 to the minus 12?
Yeah.
Or
Second-
positive 12?
Positive 12.
Positive 12, okay. S minus 1?
Mhm.
That's a fancy way of saying hertz, so there's kind of 3 different things we use. Hertz is equal to 1 over seconds, which is equal to s to the minus 1. That's a standard unit for frequency, because a frequency is like how often does it happen? Does it happen every second? Does it happen twice a second? 3 times a second? This is happening 1.8 trillion times a second. Pretty fast. So we're looking at something that is in frequency of hertz. Do you know what equation to use that relates frequency to wavelength? So in our logic, right, so let's say we're totally stuck in this and we're just like, no idea what to do. We do this thinking. Turns out there's only one thing that's implied, but if we don't know that one thing implied, this problem becomes impossible. So we need to know that we use the Greek letter nu for frequency, and that's 1.8 times 10 to the positive 12. We want to result in wavelength, that's going to be lambda. And once I have that, that's all it tells me. So whatever's being implied needs to be figured out with those 2 pieces of information. When I look at the equations sheet, there's one equation that uses those 2 variables. Let me make sure I'm not lying. There's kind of 2, but there's one that just uses those 2 variables. Do you see it?
C equals lambda V.
Yeah, not V, new. I know the scripts, none of the fonts really do the new as swoopy as I like to make it. So C is a constant. So that's it.
Speed of
Yes, speed of light. So all I have to do is 2.99 times 10 to the 8th meters per second divided by, and it was 1.8, right? I didn't miss a digit there. 1.8. What was that?
1.8 times 10 to the 12.
Okay, I just wanted to make sure it wasn't like 1.82 or something like that. Right, so notice meters per second divided by 1/2. My inverse seconds is going to cancel. I'm going to get something in units of meters. I'm expecting an answer on the order of -6 because it asks for it in micrometers. So I do 2.99 times 10 to the 8th divided by 1.8 times 10 to the 12th. Actually, that's actually pretty close. Okay, and I get a value of 1.66 times 10 to the -4 meters. Micro is -6, so I move my decimal place over twice. So I get 166 times 10 to the -6 meters, which is also equal to 166 micrometers. Right, and that makes sense. It's asking for the answer on the micro scale because the micro scale is between 1 and 1,000. Right, it's the easier place for the brain to function. Our brains do not do great with really small numbers or really big numbers. It does very well with numbers between 1 and 1,000. It does best with 1 to 100, but 1 to 1,000 is doable.
And then we just, I'm just starting to piece it together in my head. So we know because the mu is that how you?
Nu.
The little like half u.
Oh,
half
mu, yeah, mu.
And we were able to just take out the 10 to the -6 because that is
Yeah.
mu.
Yeah, so
Okay.
I'm doing those unit conversions in
Yeah.
a shorthand way, in a shortcut way.
Okay, I think that's making more sense than before.
Okay, cool. Yeah,
Okay.
and this shortcut way makes more and more sense the more we practice.
Okay, perfect. Thank you.
So I would practice the way with the fractions a little bit more.
And then go from there.
And then when you start to see, you're like, oh, I
Okay.
see. It's always like, because like if I did the fractions way, right, it's going to be 166 times 10 to the -6 meters times 1 micrometer per 1 times 10 to the -6 meters. The 10 to the -6 just disappears.
Yeah.
So my trick for doing that is I try to get my 10 to the power of in one of the common prefixes.
Okay.
So that way it just cancels out really easily.
And that's like what you did by moving it, making
Moving
it
the
one.
decimal place over
Okay.
twice so it was -6, and then I could just
Perfect.
divide out the -6.
Awesome. Okay.
Yeah,
I just have one more question.
sure.
Could you explain like largest wavelength absorbed again?
So largest wavelength absorbed.
Like
Uh,
small versus largest like.
Are we all good with this one? Good, okay. So largest wavelength versus smallest wavelength. The thing to remember is there's really there's kind of like a 3-step relationship that's going on when we're looking at this. Right, so we've got our energy scale. We've got our n equals 1, our n equals 2, our n equals 3, our n equals 4, our n equals 5, our n equals 6, our n equals 7, and it keeps going. I just get tired of drawing them. And there's kind of 3 different things we can look at. We can look at the change in energy of the atom, how that relates to the energy of the photon, and how that relates to wavelength. So the change in energy of the atom and the energy of the photon directly relate to each other. Change in energy of the atom goes up, energy of the photon is going up. The wavelength is inversely related to that. So as the energy of the photon or the change in energy of the atom go up, the wavelength gets smaller. Big energies relate to small wavelengths. Here's how I think about it. What's bigger energy? Oh, maybe this won't work. Let's slow down a little bit. What's the scale of visible spectrum?
400.
Yes. Which side is red?
400.
700.
Oh.
Red is the 700 side, purple is the 400 side. If we go past the purple, we get to ultraviolet. Is ultraviolet high energy or low energy?
High.
It's high energy. And that's a smaller wavelength. Higher energy is smaller wavelength. Infrared, right? If we got red down at 700, if we go to bigger wavelengths than red. So we're going past red to like 800 nanometers, bigger wavelength. Is infrared higher energy or lower energy?
If you're going past red,
Yeah,
so it would be lower.
it's lower energy. It's a bigger wavelength, but it's smaller energy. So there's this, again, every one of these problems, right? If it was just like plug the numbers in and give me the number that comes out of the equation, this would just be word problems in a math class. There's always some point where we have to put some logic to the physical reality and have some kind of physical, chemical phenomena that we're explaining for it to be a chemistry class instead of just a weird math class. So the process we're looking at here is, if we're looking at emission, and let's say we're going from n equals 3. I could be going from n equals 3 to n equals 2, or I could be going from n equals 3 to n equals 1. One of those is a bigger change in energy, which is going to be bigger photon energy, which is going to be smaller wavelength. One of those is a smaller change in energy, which is going to be a smaller photon energy, which is going to be a bigger wavelength. Now, if we did it for absorption, the same logic actually applies if we're doing absorption, right? If I'm going from 3 to 4, or if I'm going 3 to like infinity, smaller change in energy, smaller photon energy, bigger wavelength. Bigger change in energy, bigger photon energy, smaller wavelength. So it's the change in energy of the atom directly relates to the photon energy, which inversely relates to the wavelength. And it's that inverse relationship at the end that really messes with people.
Okay.
Which is why I'll usually draw this picture to make sure I don't mess it up, because it's really embarrassing when I mess it up in front of the class.
Thank you so much.
Hey, you bet. Any other questions before I stop the recording?
Yeah, I have like a conceptual question.
Sure.
So, what kind of values should we expect to see for like molarity or like for molar absorptivity?
For molar absorptivity, epsilon, now let me erase this thing here. Yeah, let me just erase this. If we're looking at molar absorptivity, it depends on the units we're looking at. The range that I remember is when we are in the units of molarity and centimeters. And in that case, it's approximately 10,000 to 100,000. That's what we typically see for most of the dyes we deal with, most of the colorants we use. That's the usual thing we see. The place where you have to be careful is some people will write epsilon in 1 over micromolarity per centimeter, and then it's like 0.001 to 1, 2, 3, 4, 5 to 0.1. Right? But I don't like fractions. I don't like decimals. So I always, ooh. Did I just break something? I don't know. So I always go with this one. I always put it in units of molarity, and that's the typical range we see. What was your other question?
Just on the very
I thought
subject.
I thought there was something else on top of that.
I asked about molarity.
Oh, molarity. So molarity, the problem with molarity, our typical molarities, molarity has a huge range. Most of the stuff we typically deal with in our class is going to be like 2 molarity to like 0.1 molarity. The only place where we get a really big difference in that is when we're dealing with dyes. Dyes are usually on the 1 micromolarity to like 100 micromolarity. But there's not really a typical range for molarity because it's just hugely variable depending on what kind of solution you're making, what you're making that solution out of, right? How big you're making, like it has a huge, like both of these ranges are reasonable. Anything in between those ranges is reasonable. It just really depends on the chemical system we're doing. So far, the only one we've really had experience with is the dyes, which are on the micromolarity scale. But pretty soon, when we start dealing with salt solutions, acid solutions, base solutions, we'll be on the molarity scale.
Okay.
Okay.
Sorry.
Thank you.